So this is the fourth session on signals and systems, and we are going to study piecewise linear functions in this particular session. So let us start. First of all, we ask the question as to why piecewise linear function is required. Okay, so let's try to answer that. First of all, note that there are a number of studies involved in when you study signals and systems subject, number of studies you do. What are the kind of things you do? You study how to generate signals, whether sine wave, square wave, step, and so on, ramp, etc. Then you study operations on signal like an amplitude scaling, time scaling, shifting, and so on. System properties, you study whether system is linear, non-linear, etc. Then you study the frequency spectrum of signals. Then you study frequency response of systems. Now, in order to make all these studies, you often illustrate it by examples. And for these examples, you use signals, which are simple signals. So often all these things that you study, all these studies are often illustrated by simple signals. What kind of signal? Rectangular pulse, triangular pulse, trapezoid, etc. Now, these kind of signals can be easily implemented by what are called as piecewise linear functions. And since we want to be able to make all these studies through MATLAB simulations, we would like to know how to generate these kind of signals, which are often used in the study of signals and systems. So as I said, all these can be implemented by piecewise linear functions. That is why we study this. Okay. So to give you an example, and note that we are going to study the piecewise linear functions for continuous signals, and later on we'll talk about the discrete signals. Incidentally, note that in all these sessions that I have been recording, if you want to get maximum benefit out of this, listen to the explanations of the program, enter those programs yourself, run them, verify them, and of course you can modify them whichever way you want to modify. Then you will get maximum benefit from these sessions. All right, let's continue. So an example. So suppose you have a continuous signal like this. This is a triangular pulse. Okay. So from -2 to -1, see on the x-axis you have plotted time, and as usual on the y-axis you have plotted the amplitude, which is using the variable x. Okay, so between the times -2 to -1, the amplitude remains 0. Okay, then from -1 to 0, and during this time this increases linearly. So note that from this range, as you go in this range, the equation for the line changes. Okay, then as you move forward and go between 0 and 1, you find that the slope changes, and finally it changes again here. So what is the situation? What are we trying to say? We want to generate this signal, and what is given to us? So what is given to us is the endpoints of all these straight lines. For example, two arrays are considered as input to the program. So one is the time array, and in time array all the values are not given to you. Only the endpoints of the straight lines are given. For example, -2 and -1. During this period, the equation for the straight line doesn't change, and that is why those middle points are not given. After all, if all those values are known, then you can directly plot it. The point is, endpoints are given to us for all the time periods where the straight line slope is changing, and using that we want to find all the intermediate values for the time array as well as the amplitude array. That is the kind of problem we are trying to solve. Okay, so what we'll do, we'll write a program to generate intermediate points and plot the graph. So we'll generate all intermediate points for the time vector, and we'll also generate all the intermediate points for the amplitude vector and then plot them. Now, before we are able to write this program, we study one important statement in MATLAB that is called as Lin space statement. Some of you might already know about this. Now see, whenever you want to generate points for the straight line, intermediate points for the straight line, you need to write the equation for the straight line. Now if you have to write the equation, you need to know its slope, so you have to calculate the slope, you have to calculate the intercept, and then you can implement the equation for the straight line. But the linspace statement from the MATLAB makes life somewhat easy for you, so you can easily generate all the intermediate points in a linear fashion. Okay, so let me explain this statement to you. So y equal to linspace x1, x2, n. So what does it do? It starts from x1, ends on x2, and generates n number of points. And the spacing between the points is uniform, linear space. And what is the spacing? That is x2 minus x1 divided by n minus 1. So to give you an example of this, if you execute this command linspace 0, 1, 11, then x2 is 1, x1 is 0. So numerator here is 1 minus 0, that is 1. N is 11. So denominator is 11 minus 1, that is 10. So this 1 by 10. So the spacing between the points is 0.1. So you start from 0, end on 1. But how many points you have got? You got 11 points. And what is the spacing? That is uniform, and that is equal to 0.1. So start from 0, 0.1, 0.2, 0.3, 0.4, and so on, all the way up to 1. So you can test this linspace statement by experimenting with different values of x1, x2, and n. So once we have understood this linspace statement, we are going to now write a program which will enable us to generate all the intermediate points for the time vector and also for the amplitude vector. All right. So this particular program is used to plot the 3-point function. That means my t vector has 3 values in it. First is -3, -1, 2. Understand that the signals are necessarily in the increasing order of the time. So this vector will always be in the increasing order. Amplitudes, of course, could change any which way. All right. So you got one straight line between -3 and -1. And what is that straight line? The amplitude changes from 0 to 2. And you want to calculate all the intermediate values for the time vector and also for the amplitude vector. So that gives you one straight line. Then the other is between -1 and 2. You want to generate all the time vector points. Now here it is changing from 2 to 0. So it's a straight line with a negative slope. Now the equation will be different, and you want to generate all the intermediate points. All right. This is as usual. So clear console, clear previous variables, clear figure, etc. You know that. Okay. So what is the first thing we do? We calculate the length of t. In this particular case, how many values t has? 1, 2, 3. So when you calculate nt equal to length of t, the nt will hold the number 3 for this particular example. Then you generate ts, that is the sampling time. Why do we need sampling time? Because we want to generate the intermediate value. So we need the sampling time. Now remember, when we studied the generation of a sine wave, what we had done was we had taken a sampling time which was very small compared with the time period of the sine wave. In this particular case, the signal that we have got is not a periodic signal. However, the total duration of the time we know, and we can generate a sample time which is quite small compared with this. And how do you calculate the total time? That is easy. What you do is take the last value and from that subtract the first value. So t nt, remember nt is 3. So you are calculating t3 here, that will be equal to 2. Minus t1, which is -3. So when you do this calculation, you are actually doing 2 minus -3, which is 5. So 5 seconds is the total time period for which you are doing the simulation. And what we want to do is to choose a sample time period which is much smaller than this. So you can choose a very large value. In this case, I have chosen 100. You can choose 200, 300, 400, whatever. Of course, the larger the larger the number you choose here, it will mean more calculations will be done. But 100 is a reasonably good number, so I have chosen that. All right. So the point is, once you have chosen TS, then you will be able to generate all the intermediate values for the T vector and also correspondingly for the X vector. So let us now do that. So T1. Now T1 is different than T because this holds only 3 values, whereas T1 will hold all intermediate values. And how do we do that? We start from T1, provide the increment Ts, that is the sampling time, remember, and end on T2. Why do we end on T2 here? Because between -3 and -1 you have one slope and then the slope changes. That is why you want the equation for the first line. So you go from T1 to T2 with an increment of Ts. Okay. Then, so here you have essentially generated all intermediate points for the time vector. Now similarly, you want to generate all intermediate points for the amplitude vector between 0 and 2. So now what do? You find the length of T1. So length of T1 will give you number of points for the time vector. And you also want to generate the same number of points for the amplitude vector, and the reason is that whenever you are making a plot for later on, for example, we'll make a plot of time versus y. When we make that plot, it is important that the number of points in both the variables must be same, otherwise you can't plot. So we are using this n1, that is length of t1. And now what do? Linspace x1 comma x2, so you go from 0 to 2. And how many intermediate points? How many points? That is n1. Okay. So you have generated the y1 vector which corresponds to this range. Now you want to repeat this for the second range because the slope changes now. It's negative slope. So what do? So T2. Now start from T2. Okay. So that is again -1. So then Ts again and go up to T3. So you generate all the intermediate points. At this point you might note that there is some repetition of this T2 here. It's used here and it's used here also. So you might get a very small error in timing, but that time error is small because the sampling interval we have chosen is quite large. It can be eliminated through a little more modification of the programming, which I can leave to you. Just now, to keep the program simple, I am just saying from T2 you go to T3. Now what do? You find the length of this, the number of samples in this. So N2 is equal to length of T2. And then Y2 is equal to linspace x2, x3. So again you find that x2 is repeated here. So you get a small error in the amplitude vector as well as a time vector. But it's not very significant because the time slice is quite small. Okay, so at this point you have generated y1, y2, t1, t2. So what you can do is you can concatenate them. So y1 followed by y2, t followed by t1 followed by t2, that will give you t vector and you get the y vector. Notice that we have 3 points here, but the number of lines obviously will be one less than the total number of points you have, because you start from the first point and you require at least 2 points for drawing the line. So that is why you find that although you have 3 points here, the number of arrays for y will be 2. y1, entire y of course is single array, but it's obtained by concatenating y1 and y2, and t is obtained by concatenating t1, t2. Concatenation means simply place this array after this array. That is what it means. Okay. So now once we have got our t and y, we have to plot it simply. So that is straightforward. Plot ty. This is as usual. These commands we have studied: line width, x label, y label. X label is time, y label is amplitude. Then you provide a title, a 3-point function, font size, grid on, display ts. Okay, this display I had written just for checking. That's what is the value of ts. In fact, in this particular case, it will be 0.05. It's not really required in the program. I had put it just for a check. Okay. So now when you execute this program, this is what you will get. So from -3 to -1, you got a line with a positive slope and going from 0 to 2. And then from -1 to 2, you get a line with a negative slope changing from 2 to 0. All right. Now, one thing I would like to point out to you is, so let me go back to this program. Uh, when we have obtained the all intermediate values for one line, you essentially repeat the same thing for the next one. Now in this particular case, we needed only two vectors which had to be concatenated. But if you have more, suppose 4, 5, etc., then it will be laborious to simply repeat this. So it is much more elegant to write a function, and when you write that function to which you pass these parameters and generate all intermediate points, that is what the function is going to do. I'm trying to tell you that when you are writing that function, some of the early statements would be similar to this. Okay, but when you are generating your t1 vector and y1 vector, what you can do is you can put a for loop. So you can, for example, this one can be changed with so I equal to 1 to nt minus 1, and then this will be I plus 1. So in that for loop, this will be calculated, this will be calculated, and if there are more number of points, all the remaining vectors also will be calculated, and you can put them. All right, so this we have already discussed. So now we want to study that general function. So we have taken a slightly different example here. Suppose we want to generate a triangular pulse, and again note that what we know is only the intermediate points. Okay, so t vector -2 to -1 is remaining 0. Okay, then from -1 to 0, -1 to 0 is changing from 0 to 1. Then from 0 to 1, it is changing from 1 to 0. Okay, 1 to 0. And finally it remains 0 from 1 to 2. So it remains 0 in 1 and 2. So here, what I have explained is really the calling program. That will tell you how easy it is to use once the function is developed, how easy it is to use. All you have to do is to give the endpoints of all the straight lines for time vector as well as the amplitude vector. Simply call the piecewise linear function, which I have named as PL, okay, and pass these arrays. So this t is passed, x is passed, and what it returns is y and t, where y is the amplitude vector having generated all intermediate points, and t is the time vector having generated all the intermediate time vector points. All right, so let's now see the function itself. So function ytx equal to pl ta xa. So when you call this t and x go into ta and xa, and it returns two arrays y and tx. So as usual, remember that brute force program that we had written. This was the first statement we had written, and t was length of t. In this case is ta. So length of ta. Then what do? Calculate ts. So ta nt minus ta1 divided by 100. Now before getting into the loop, you must initialize the loop. So you start with the value of y, that is xa1. Y is the return value. So you start with its first value, okay, whatever that is in this case it's 0. Then also start with the first value of the time vector, that is ta1. Now get into the loop. So for I equal to 1 to nt minus 1, note in this case, see, this particular function will not work if you provide only one value. Obviously we are generating a piecewise linear function, and a line cannot be drawn just with one point. You need at least two. So I am assuming here that you will have at least 2 points, but you can have more. So for example, if nt is equal to 2, then it means that you have just 2 points, so just one line, so it will go from 1 to 1. In this case, you have actually how many points? 1, 2, 3, 4, 5. So in this case, with 5 points, you will get 4 straight line equations, so that is what you need. So I equal to 1 to nt minus 1, so it will be repeated 4 times, and you will generate all these 4 vectors, concatenate them, and so on. All right, so now ty, this is the time vector that you generate. So tai, ts, ta, I plus 1. Okay, the next value, that is from here to here, and all intermediate values are generated here. Then you calculate the length of this ty, okay, and use that length in order to calculate the value of y which is to be returned. Don't confuse this x with this x, because this is local to this function, so there is no confusion between these two. This is the actual value of y with all the intermediate points that we have obtained. So first time you do it, all the intermediate points from 0 to 0 will be obtained, and so on. And then you concatenate with the initial value of y, that was xa1, and then go to x. Then do tx equal to similarly tx, ty, and end. So these were the for loop ends, and then of course this is the end for the function. Alright, so when you call this function and execute the calling program, this is the output that you will obtain. So when you solve problems from signals and systems, often you might find a waveform like this, and suppose you want to do convolution operation on this. So later on we'll study convolution, and we'll study how to do it analytically. But having done it analytically, if you can test it by simulation, it will be good. So what you can do is, this triangular pulse you can generate by using this function, and then there is a convolution function available in the MATLAB. So use that and then check whether the shape of the convoluted output that you are getting through MATLAB, whether it is same as the one that you got from the analytic method, paper and pencil method. All right. So this particular session has explained to you how to use the piecewise linear function, how to write the program for it, and how to use it for generating different kind of small signals which can be expressed in terms of piecewise linear functions. And that's all in this session.